Okay, let's talk shop. How's everybody doing today? Good, good, good. Okay, so let's say, so we've already done this experiment where we looked at dispersions of light. So we know that white light can be diffracted into all of the different colors of lights, right? And so we have the lower wavelength, which is around the blue area, which is seen on here, or purple for us. So the purple light is going to be about 300 nanometers. So purple light is going to be about 300 nanometers, and then red light is going to be about 700. Green light is going to be about 550, if I remember correctly. Yeah. Okay, now you have these options, right? And knowing what you guys know at this point, we're going to have a higher energy system. Put it on the board. I've got to change the system instead. Okay, so I'm going to give you guys some equations that we're talking about. Oh, by the way, higher energy system. First, how do you really? So good. So this is your quiz. I'll give you guys, we'll say 15 minutes. That's more than enough. You have to do one calculation, maybe two. Okay? You guys ready? Anybody know? Look at your notes before coming to class. Yeah, no, maybe. Okay, so we also know that when we have the lines very distinct, that's called line spectrum. So this is an example of a line spectrum. All right, can you guys all see that? And we saw that when we excited the different elements that were in those tubes, right? And you also kind of saw it when you guys excited the chemicals. We actually put fire underneath them and you saw the different colors. You're like, woo, yellow, woo. You remember that? Okay, good. Now, we know that this has to do with the excitation of electrons. And we know that, like, in this case, this would kind of represent hydrogen, right? We know how many electrons does hydrogen have? One, all right? So why do I have multiple colors that are coming out if I only have one electron? Want to gamble? Yes. Okay, any guesses? Okay, so let me tell you why. Okay, so the electron can be excited to different energy levels, right? And so since it can be excited to different energy levels, then when we release that energy, we're going to get a different photon. Okay, so that one electron, so one hydrogen may be excited to one energy level, another one's going to be excited to another energy level. So they're going to be excited to different energy levels. Okay, so that's the reason why. But the thing is that there's a limitation because there's only so many energy levels that it's going to be able to be excited to with that range of energy. Okay, does that make sense? And we'll talk more about it, and we'll start clicking here in a minute. Okay. Okay, so here's line spectrums for hydrogen, mercury, and neon. Line spectrums are also called excitation spectrums because you're exciting the electrons. Okay. So this brings us to Bohr. Bohr was the scientist. How many of you guys saw Oppenheimer? One. You should go see it. It's a really good movie, right? It's also historical and a little bit, a little bit more. And it goes to chemistry and physics and stuff like that. So it's pretty exciting. And it talks a lot about the stuff that we're talking about today. Okay? So Bohr was a scientist, and he basically had established this model. He made leaps and bounds by establishing the model for the hydrogen atom. And so what he basically did, he said, of course, the atom has the nucleus, right? And we have electrons that are traveling around, right? He says it's orbiting the nucleus, okay? Now, most of the electrons are going to be in space. Now, this is what people had already established. They had already contributed to this concept that the majority of the atom is in space because these electrons are really tiny and they're traveling that dense nucleus. That's, And so the bulk of it is empty space. Now, what Bohr was saying was basically that there are energy levels, right? And this electron that's orbiting can orbit in different energy levels. And those different energy levels, they're going to be quantized. They're going to be discrete. They're going to represent those lines, okay? So there's only a limited amount of energy levels that it can go to, right? Compared to what we saw with white light, which is continuous. So here's an example, right? So the very first one, the ramp, that represents the continuous, right? There's no steps that you have to go over to get there. Now, what Bohr was saying was that there's very distinct energy levels. There's steps. There's that first step of energy level. There's the second step of energy level. There's the third step of energy level. And that electron, it starts off at ground state, but it can be excited to different steps of energy level, depending on how much energy you put into it. So, this is Bohr's model. Can you guys see the nucleus in the middle? See my nucleus, that little nucleus right there, right? And then here, for the hydrogen atom, it's only one electron, so when it's at ground state, it's right here. We call this N1, or we call it our first period. Oh my God, did you guys say period? What does period mean to us? What does period? Look at our periodic table. Periodic table. What does period mean to us? He's looking for his periodic table. Right next to you. What does it mean? If I tell me what period I'm in. Never there. Tell me. What does it mean? The rows, right? Okay, so we know it's going to be the rows on our periodic table. So these periods represent those rows on that periodic table. So we have period 1, period 2, period 3, period 4, period 5. They're also representing the energy level that we get to get excited to. Those electrons get excited to. So we know that ground state for hydrogen is period 1, right? It can be excited to period 2, period 3, period 4, period 5 by putting energy into it, right? And then we know it gets excited, what has to happen at some point? What was that? It has to go back to 1. It has to go back to ground state. It has to drop back down to ground state. Because excitation is only temporary. It's not permanent. Now, how many of you guys watch quantum theory? Or quantum, what's it called? Quantum Leap. Anybody watch Quantum Leap? You heard of it? It's a TV show. Watch it once, you may like it, you may not, you know. Anyway, it's been rebooted, it's current right now. So the concept of quantum leap is the fact that if we excite every electron in your body to the right energy level, we can send you, in that show, you can send them to a different time and a different place, right? But in theory, you can send them to at least a different place, right? So for instance, how many of you guys eat turkey for Thanksgiving? So, do you cook it? No? You cook your turkey? Okay, but you eat it though, right? Okay, good. So, in theory, if we excite every electron in your turkey, right? That's in your oven. We can excite it so much that it will end up on my table. Right? But the problem is that to get that excitation to the right point is what we don't understand. So that concept of teleportation, moving from one place, one location to another location instantaneously, is potentially possible if we learn how to excite those electrons right and not cook you at the same time. Right? So quantum theory is based upon that excitation and then also dropping down to that ground state. But the problem is that we drop back down to ground state. So if we were able to do it, guess what would happen? It would appear on my table for a split second or less than that, and then it would drop back down to back into your oven, right? So it could be happening and we don't even know. Right? Just get excited, you know. And you know, you think you see something, maybe you really do. Right? I may. Let me check. You need one too? Yeah. Anybody else? They have to give you an IOU. Okay, so that is the concept of quantum, and that's why Bohr was like this big, huge, big deal. It also helped us understand the hydrogen atom, right? And so, do you guys remember the atomic bomb? Remember about that? So that's what this all kind of deals with. It's that energy that's being stored in those electrons, and exciting them can cause effects, major effects. Okay? No. See, we're talking about the quantum leap. Okay, so quantum leap basically means that we can go from one energy level to another energy level. And we don't have to pass through that second one. So if we're starting out at 1, we can go straight up to 4. We don't have to worry about passing through 2 and 3. There's no route, right? So that's that concept. So that is also the concept of teleportation, right? To teleport, I can teleport to Kalinga without having to go through Mendota and through Third Rock or 5 Rocks or whatever it's called. I can't remember. Something rocks, right? 3 rocks. It was some number rock, right? Okay. So and so that is the concept, right? And we've been working on trying to figure this out. And I'm hoping that since you guys are learning about this, you guys will be interested. And one of you guys figure it out. Because if you make a lot of money, you send it back to the college, then I make a lot of money. You know, see how that works? Okay, good. So we know that excited electrons are unstable. Kind of like those kids when they have too much candy. They're unstable, right? They're hyper, they're all over you, right? You just want to smack them and everything, right? Which obviously don't do it, okay? So we want to know you have to get back down to ground state, right? So you get excited, at some point you have to get back down to ground state. Kind of like crackheads, you know, they get excited when they're on their stuff, right? They're all crazy and everything, and then they hit that low again, they're on, you know? So this is basically showing you what we've talked about. Here, we're exciting the electron. It starts off at ground state, we put energy in, right? And guess what? The law of conservation says we have to get energy out. So it has to emit energy. Because we know that excited state is not a stable state. It has to come back down. Okay? So again, this is Bohr. Now Bohr introduced us to the quantum numbers, right? There are 4 quantum numbers. The very first number is called the principal number. Okay? Now, you guys are not going to have to know about the quantum number, but you're going to have to know about electron configuration. Electron configuration is basically putting an address on every electron that you have, keeping track of every electron that you have in and out. And I'll show you how to do that in a minute. Okay? So the principal quantum number, we call it N, is always going to be our period. That's going to be the first thing that we're going to start off with. Okay? So then the next quantum number is going to be the sublevels. Sublevels, that's going to be our S, and I want you guys to write this down, our P, our D, and our F. Okay, so we're going to take a break from the slides here for a minute. Now you're going to have to listen and write stuff down. So we're going to be writing it down on the side. You guys are going to listen, right? Can you handle it? I'll put it on the board for you. Okay, so we have the S, the P, the D, and the F. Now again, this all has to do with electrons. We're trying to keep track of all the electrons that we have. Okay. Now, the S sublevel can hold. So we'll say electrons can hold. The S sublevel can hold 2 electrons. The P sublevel can hold 6 electrons. The D sublevel can hold 10 electrons. The F sublevel can hold 14 electrons. Can you see a pattern? What is a pattern? What was that? It increases by 4 electrons, right? Okay, so we know that it's increasing by 4 electrons. So the thing is that, didn't I tell you that science is changing? Science is constantly changing. And we've got to be prepared for that change. As chemists, we're prepared. Because technically we can have a G. So F, G, and H. In theory, we can have those sublevels, right? We don't have enough electrons, and we don't have enough elements for it yet, but we will one day. One day we will. Okay? So if I had G, how many electrons can it hold? 18. And then if I had H, how many electrons can it hold? Okay? Now, the thing about it is that we have these electrons, they're held in groups of two, right? And we call those groups of two orbitals, right? And so you have to have an electron that's in a positive spin and one that's going in a negative spin. They have to be opposite of each other to kind of balance each other out, right? If they're twos. You know, you can have one in that orbital, but you only have one in that opposite spin. At some point, it wants to try to get that other one filled, or it'll lose it, right? Or it'll try to lose it one or the other, right? It doesn't like to have that lone electron by itself. It likes it in pairs, okay? So we kind of have to think of them in love seeds, right? Pairs, right? You know what a love seed is, right? What is a love seed? It's a couch that can hold two people, right? So we want to think of it orbitals. They hold the maximum of 2 electrons. So, how many orbitals would you expect the S subshell to have, or sublevel to have? 1. What about the P? P. Okay. P. Not D. How many? 3. What about the D? And the F? The G? 9. And the H? 11. You see a trend? Right? Okay. So we know that orbitals can only contain 2 electrons. So the P sublevel has 3 orbitals. The S sublevel has 1 orbital. Okay? So basically what that means is that electron is able to sit there and rotate in that orbital. Okay? So at most you can have 2 electrons rotating in an orbital. Okay? Does that make sense? So there's 3 different orbitals for the P sublevel. So the way that we define those are, we call it PS, PY, and PZ. Now, when we get to 5, it gets a little more complicated. Because you know that it's a 3D structure, right? It's going to be a 3D structure. If you have 1, you're going to have 1 in the X direction, right? X direction is typically like horizontal, right? Y direction is like this, and then the Z direction is like this, and the Y direction will be like this, right? So the 3D structure. We're looking 3D, okay? You guys are looking at me like I'm crazy. I am not crazy, maybe a little bit. Okay, so my box here. Isn't this 3D? 3D? Okay, so in theory, a flat piece of paper would be, it would be X and your Y. Flat piece of paper. Your paper's flat, right? You have an X and a Y orbitals there. Now you have a Z. That gives us 3 dimensions, right? So we have an X, Y, and a Z that's going up. So that just makes it 3-dimensional. Okay? If you think about a cube. Okay. So let me draw that on the board because poor people at home are thinking, man, crazy. So this is X. This would be X, and this would be our Y. Okay? And then Z would be, this would be our Z. Okay? So it gives us that 3-dimensional structure. Okay? So we have orbitals in both those directions. Now, when we're talking about the D's and the F's, they get a lot more complicated, and I'll show you some real pictures here in a second. Okay? How you guys feeling so far? Okay, so here's a rule. What is the maximum electron? I'm going to ask you a question. maximum electrons that the S subshell can hold. What is the maximum? 2. What is the minimum? 1 or 0, right? You can take a little 0, none, right? None would mean 2. You got 0, 1, or 2. That's it. Now, what about the P sublevel? We can have 6, right? Maximum. So, the first thing that you should look at when you're looking at electron configuration, make sure you're not above your maximums, right? And I'll show you an example of that in a second. So we can get a little more information. Okay? Go back to the top. You guys need a potty break? You want a potty break? Or are you guys good? You're good? You look good. Well, you look tired, but you know, she's getting her coffee now. She's getting her pick. She's like, ooh, got it. Okay. So we'll keep going and then we'll wait a little bit for that coffee break. Okay, so the principal energy level, if you guys can do me a favor, look at your periodic table. What is the lowest value you can have? What is the lowest period you can have? Lowest period is what? 1. Right now, as of today, our largest period is 7 right now. So we're limited right now, right? But there's the potential of getting more, right? As soon as we start finding more elements or make more elements stable, then we can have more. And you know, don't limit yourself, because they used to say, well, these are the only elements. At the beginning, there was like 10, right? Then we went from 10 to 118, right? So don't limit. You know, you guys may be the ones that actually find the next elements or find how to make them stable, right? Synthetically made. So we've talked about the S, the P, the D, and the F. You guys are comfortable with that so far, right? So when we're starting to write electron configuration, what we do is we have to put the period that we're in, and then we want to put the sub level. And the last thing that we're going to be putting is the number of electrons that we have in it. Okay? So if you guys take a look here, right? We have like 4s, right? What is the maximum that the 4s can hold? Electrons. That's right, because it's the S, it can only hold 2, right? So we know that the 4s, at the most that we can have, we're going to have a superscript that says 2. Get on the board, there it goes. Okay, don't make fun of my 3rd grade handwriting. There we go. So we know that the maximum it could have is 2, right? It can have 1 or it can have 2. If there's none, we don't put it there. Okay, does that make sense? Okay, so every sublevel has to have a period to let us know which one it is. Okay, does that make sense? Because you have to tell me. It's kind of like you're giving me an address, right? You don't tell me, okay, you're coming, I'm coming to pick you up, right? You don't say, go to Fireball. That ain't gonna tell me anything, right? Because there's a lot of places in Fireball. You have to give me a little bit more, okay? So, in terms of energy level, right? The S is going to have a lower energy level. For the same period, the S is going to have a lower energy level than the P. The P is going to have greater energy than the S does. Okay? And then the D is going to have a higher energy level than the P. And the F is going to have a higher energy level than the D. Okay? So your energy level is going to increase depending on about how many electrons you're able to hold. Does that make sense? So when you're filling in electrons or filling up electrons, you always want to go. You fill up your S first, then your P, then you get to your D, and then you get to your F. Now, there are gonna be some changes there in a minute, and I'll show you those changes, and they'll make sense. Okay, so here is an example. So in terms of energy, the 3D is going to be our, in this case, the 3S is going to be lower than our 3P, which is going to be lower than our 3D. Now you'll notice, then you have the 4S, right? Now this here is a little anomaly, right? They call it, what's the word? Starts with the D. It'll come to me in a minute. But basically, the 4S is lower in energy than the 3D. So we fill up the 4S first, and then we'll fill up the 3D, okay? So you always fill them up by the lowest energy level, and then you move up from there. Does that make sense? And I'll show you what I mean by that here in a second, I promise. Because you guys are all looking at me like I'm crazy, okay? And then it goes, if you look, it's 4S, 4P, 4D, 4F, okay? And then if we hit the 5, I'll show you that. So if you guys can do me a favor, pull out your periodic tables. You need your periodic tables for this part. So we're gonna go to the periodic tables because then it'll start making a lot more sense because you'll see what I'm talking about. Okay? So let me pull up my periodic table. Give me 1 second. If you look here, these numbers here, they actually tell you the order of everything. So this here would be I usually don't teach this part. Not for you guys. So this here is going to be the first period. This here is going to be the second period. This is going to be our third period. This is going to be our fourth period. This is going to be our fifth period. And this is going to be our sixth period. Okay. So if we go ahead and write this, right, it'll be, we know that the 1s can only hold 2 electrons. Then we have 2s. It can hold 2 electrons. And then we have the 2p, which can hold 6 electrons. So that'll be a total of 8. Okay. And then when we get to the 3s, we have 3s, we have 3p, and we'll have the 3d. So you can hold 2 here, you can hold 6 here, and you can hold 10 here. Okay. Then we get to the 4s. 4, we have 4s, 4p, 4d, and 4f. Oh, by the way, add that up, that should be 18 electrons, right? So that's how you get good for 18. Okay. So here I have 2 in the S, 6 in the P, 10 in the D. That's my 18 plus groups. And then I have 14 in the F. Right? So that should be 18 plus 14, isn't that 32? Right? And then I have to come down here. So then we have the 5S. We have the 5P. Which is 6. And then we'll have 5D. Then we'll have the 6S. So that would be our 6S4. Oh, yes. Perfect. Salt is good. You never go wrong with salt. Sweet or salt, it never works. Okay, so the reason why is because normally you would think of it having 2 in the S, right? So it likes to have a stable feed shell. So by filling it up, it makes it stable, right? And that's lower in energy than for it, not for everything, but for it, it's lower than energy. And that pretty much works for all the ones that are here. For all of these guys here, they do that. Okay. And so when they're at that one, they'll still from the other, right? And then the same thing happens with these guys here, or these guys here, they'll do the same thing. They'll take one because they prefer having one in each of the orbitals than having 2 in the S and then, 4 and have that one that has to kick over with somebody else. Yeah. Yeah, and so it's a hard question. So typically on the exam, if you give me this, I'll give you the points, right? If you give me that one. But if you give me the one where you have S2, then I'll give you the points too, because those are harder exceptions to remember. And for what you guys need to know, you just really need to know location to kind of help you with reactions and stuff, right? And so, and the reactions was that right here. We're talking about the space here. It's not empty, it's being occupied by that 4F. So that's what that is right here. So you've already accounted for that. Okay, so, and I'll show you what that looks like. Okay, so everybody's back. We're early. You guys are early. You guys are quick. I'll give you guys a couple minutes to unwind, chill, because you guys are back a little too early. So. So not too bad so far. Watch videos. Videos will be up. I need to put some more up on you guys. Yes. Yes, you have a tutor online right now, and then you can have a tutor face to face. So if you go to important links, I'll show you where it's at again. If you go to important links, it has, oh shit, it doesn't. It will have the tutor's hours and their links. Okay. And they also send you emails. So you guys have probably been getting emails. Look at your emails. They send you emails that they're of their tutoring hours. I'll remind them to send you guys an email. Okay. Yeah, I got to check to see if I did. Oh, wrong class. Oh, I do. There's the right class, the wrong class again. So this is what happens when you have way too many classes. I can't keep track of where I'm at all the time. Like this morning, I got up, I almost drove to Cleveland. I was like, oh, it's today. What time is it? I have to control myself. Oh, I do. Imagine that. Okay, so just a reminder, you brought it up. I am not totally crazy. Partially, but not totally. Okay, so I have my office hours, and then down here, I have 2 tutors that you're able to access online. We're trying to get another one hired, a physical tutor. Plus, we do have one that is here on Thursdays. I believe she's here from Thursdays from 10 to 2 o'clock. Yeah. Maricel? Yeah. What's that? Yeah. Yeah, I strongly recommend. She's good. She's really good. She'll whip you into shape. What's up?
Her hours are 11 to 3.
11 to 3?
Yeah.
Okay, my bad. 11 to 3. Sorry, I thought it was 10 to 2. It was close. So it was a little off. So I also need to put hers up there too. But you guys have that. And then I'm trying to get Adam. He was in the class last semester or in the spring as well. And he's really good. But we're getting his application through the process. Unfortunately, it takes a minute. Okay, so these are the links. All you have to do is click on those links during those time periods, and they should be there. If you have any questions, you can also email them. I will attach their names with their emails so that you'll be able to email them. But you can also email them through Canvas Shell. They're on your shell, so you should be able to email them. So that's Israel. He does it Thursday from 7 to 8 p.m. online via Zoom. That's the Zoom link. And then Angelia does it from, well, she does it a couple of times. And so if you want to hit her up, they're good. So Angelia is working on her chemistry degree at Fresno State. And then Israel is working on his chemistry degree in San Francisco State. So they can give you guys a little insight to my class and to me. So they've had me for a lot of classes. Okay, questions? No questions, concerns? Okay, so let's get started. Let me tell you. Let me preach to you about electron configuration. Can I erase this? You got that? Okay, so the simplest way to understand electron configuration is to use your periodic table, right? Because your periodic table is based upon electron configuration. So one thing that I want to point out, and I think I pointed this out to you before, the periodic table doesn't really look like this. There's one other thing that happens. This is what the periodic table really looks like. Okay? So if you guys look, can you guys do me a favor? Count how many electrons are in this column. I mean, how many columns are over here? In that tower, that first tower. How many columns do we have? Let me help you out a little bit. Right over here. That's the tower that I'm making reference to. How many spots? How many columns do we have there? We have 2. What sublevel holds 2 electrons? Which one? The S. So this here is going to represent the S. I make a little lowercase s or a cursive s. Did you guys recognize that as my cursive s? I'll just make it like this, but you guys are looking at me like I'm crazy. Usually only one person looks at me like I'm crazy. And we know that the maximum it can have is how many electrons? 2. This tower over here, this here represents, count how many electrons? I mean, how many columns? 6. So which one has 6? P. This one here has how many columns? And then this one here. $14, okay? So, I wrote 10. What does the one that has 10 represent? D. So we'll put a D there, so 10. And then the one that represents 14? F. Okay, so this is what the periodic table really looks like. The reason why we take that last row, those last two rows, and pull them out, is so it fits on an 8x10 piece of paper, right? And so it makes it a little bit easier for us to see. You can see everything there. Okay, so but this is what it looks like. And so this is going to be the order that you're going to be putting electrons in. So let me show you what I mean. So let's say that we're working with phosphorus, right? Okay, now the way that we would do the electron configuration, check this out. So we're doing electron configuration. Okay, so the way that we would do this is that we would start at 1, at period 1. So every electron has to be accounted for that's in phosphorus. Phosphorus has an atomic number of what? 15. How many electrons does phosphorus have? Phosphorus has 15. So the way that we account for every electron, we're going to be putting them in the order based upon periods and sublevels. Okay, so we write down the element that we're talking about, phosphorus. We're going to use a colon. And I'm actually going to show you two ways. I'm going to show you the hard way, and then I'll show you the easy way. Okay. So we'll start here. And I should also tell you that helium, for electron configuration purposes, is really located over here. So it's that second one here. So it should be right next to hydrogen. Okay. This is only for electron configuration. So then we have 1s, and the s orbital holds how many electrons? 2. So we're going to write 1s2, right? And so that's going to represent the electrons that will be here, and the electron that will be here, where that helium is going to be. So it represents, we're going to get rid of that guy as well. So, okay, so that's 2. Okay. Get rid of that slash so we know that it counts out. Okay, so then we go to the next level. Next period. Okay, so then we go put the number. And then how many does the S have? 2. So then we're going to go 1, 2. So that's going to represent 2s2. Then we're going to travel all the way to the other side, right? Because this is still in our second period, right? And this guy represents what again? These 6 represent what? P. So then we're going to write, since we're still in the second period, we need to write a 2 first. 2p, and it holds how many? 6. So then that accounts for okay. And then we go to the third period. Okay, so third period, first one is going to be S. And then how many does it hold? 2. So we write 3s2. And you want to pay attention to superscript and subscript because if you start writing things funny, they mean different things. So, okay. And then here, we're going to go all the way over to the other side. And that's 1, 2, 3. So then we go 3p3. You guys see that? Okay, now I think of this as the harder way because there's an easier way to do it and something that saves you time. And I'm all about being easy because I'm lazy, I'm not gonna lie. If I could get paid just by coming in, saying hi to you guys and then leaving, I'd probably do it, right? So I could just do something else with my time, right? So other than hang out with you guys. I like hanging out with you guys, don't get me wrong. Not 8 o'clock in the morning though. Next time we should tell them about 10:30, that would be a good support. So. Okay, so let's see if we can do the easy way. So the easy way, what we would do is we use P again, and then you go to P, and then you find the nearest noble gas that is before P. So you look at the atomic number. What was the atomic number for P again? 15. So what would be the atomic number? I mean, what would be the noble gas that would be before P? Neon. Okay, so we know that because it has a smaller atomic number than our P, right? So we're going to use neon. So we're just going to write neon. Now, what that does is that means that we're telling our reader that we have all the electrons that neon has, right? So we don't have to write these 3 sublevels, right? Because that is what is represented by neon. So then we just go right after neon, and then we'll go 3s, s2, and then 3p3. And you can only use noble gases because noble gases, they're like a core. They're stable, right? And they represent like a core. I like to think of them as, do you guys have a savings and a checking account? Okay, so they're kind of like your savings account. You're not supposed to take anything out of your savings account. You're supposed to leave it alone. Your checking account is the account that you use to pay your bills and to go buy pizza and to take your girlfriend out, right? You don't touch your savings account, right? You guys all know that, right? That's why I have nothing in my savings account. I never put anything in it. Damn it. That's what I'm messing up on. Gotta remember to do that. So it's kind of like a savings account, right? You're not gonna touch it. So you're only gonna touch the ones here. So when we do chemical reactions, these guys become available for chemical reactions. These are the ones that you're gonna use for your chemical reactions. They're gonna be called our valence electrons, okay? We'll talk more about that here in a minute, okay? So again, these are the ones that you're going to be using for your reactions. So electron configuration is important for us to understand which electrons are going to be able to be used, because that will affect how things react, right? If we know how many that we know that we're able to use. And we have to remember that we have some of them locked up in safes. They can't be used. It takes a lot of energy to get them out of that safe, okay? Or out of that savings account, okay? You guys see that? You understand that? Okay, so let's say we had, let's do iron. Actually, let's do manganese. Okay. Now, the thing about the d orbital actually, even though it's in the 4th period, it is actually going to start off at the 3rd. So it's going to start off at 3d. Even though we're in the 4th. So that's going to be our 3d. This is going to be our 4D. And then this down here is gonna be our 5D. This is gonna be our 6D. And then the F over here, this is gonna be our 4F. This is gonna be our 5F. It's called degeneracy. That's what it's called. So the fact that it drops down one number than what it's on, that's considered degeneracy. And that has to do with the energy levels. So 3D is actually lower, I'm sorry, 4S is lower in energy than 3D is. Okay? So, everybody sees how this is done. So what I want you guys to do is I want you guys to give me the long version for manganese. I'm gonna erase what I've done. Everybody got down what I did? I want you to give me the long version of manganese. And then we'll go through it together. Actually, give me one better. Give me the long version and give me the short version. Yes. What do you mean by the different? It's the same. No, but it's still the same. Yeah. So they're the same periodic table, right? So what you're seeing is exactly the same, but I'm just telling you that here, even though that this is the fourth period, right? And this technically will be the fourth period, this year actually starts off at the 3D, right? So you just need to know that it's degenerative. So D and F are degenerative, meaning that they start off at a lower number than what they're at. So they're one lower, so D is gonna be one lower than the period that we're starting off with. And then if you look at F, F is two lower, because this is 6, and that's, so you just wanna remember that it starts off there. Does that make sense?
Yeah.
So I'm also gonna shift it to a normal, your periodic table, so you guys can see what it looks like normal. Because this one is, I like it, but it's not what we got. Then I'll adjust everything while you guys are doing that. You guys ready? Good. Manganese. Okay, so where are we gonna start at? One S two. Okay, so then that's gonna represent there, there. And then two S two. Okay, so then that's gonna represent here. 2P6. That's gonna represent here. Yes, we're so fast. 3S2. Okay. And then you have to go across. What is this? 3P6. Oh, you said it? I'm sorry, I didn't hear you. And then chorus 2. And then 3D5. Okay, questions? So then the short way, how would I write it? Okay. 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 Questions? Okay. Good. Okay, so now I can tell you about some exceptions. She gave it. Did you hear me? I said I have to tell you about some exceptions. So now she gave me that look. It was a different look that she gave me earlier. Okay, so there are two rows or two groups that are going to give you exceptions. Let me give you those right now. I'm going to erase. Can I erase this stuff up there? Can you guys? Okay. The exceptions are going to be row 11, or say group 11, sorry, not row, group 11 and group 6. Now, these guys, they're going to want to try to be stable as they could possibly be. So what they'll do is they'll actually steal one of the electrons from the s orbital so that they can either have 5 electrons in the d orbital, because 5 electrons is better than having 4, right? Or having 10 electrons in the d orbital, right? So let's say we had silver. We're going to do silver. And we're going to do it the short way, okay? So I want you guys to give me the electron configuration for silver. And then I'll show you what it actually does. The short way. So that's often called the noble gas core method. Okay, so what would be my core? said KR, right? Yeah. Okay. I wasn't sure if you said AR or KR. KR. Okay, and then so this is what we would expect it to do based upon how things were ordered. But what it actually does, it steals from the S and it puts it in the D. Because then it allows that one to be, since it's in the lower period, it allows it to be stable, more stable. So in that case, the answer really should be AG. KR. 5S1. 4010. Okay. Questions? Okay. Now it only does that. Yes.
Why is it 4D and not 5D?
What was that?
Why is it 4D and not 5D?
Not 5D? Because again, the d orbital is degenerate. You always start one less. So yeah. So the thing is that if you looked, we'll go back. So here, so we have 4S, we have 3S, we have 3P, and then we have the 3D, right? In terms of the energy level, the 4S is actually lower in energy. So when we're putting electrons in, it'll go to the 4S first, and then it'll go to the 3D. Okay? But the thing is that it's lower in energy, so they're overlapping in terms of the energy level. It's a little bit lower than the 3D. So that's the reason why we put the 3D after the 4S, right? So, and that's the reason why it's degenerative. And that's the same thing with the F. Exactly the same thing with the F. The F is 2 below, right? So when you're in the 6, you start off with the 4F. Yeah, and so that's why I had you guys put 4F at the bottom and 3D, so it'll help you remember that. Okay. And let's see. Okay. So the thing is that once it does this, once it puts it in a D, it makes it stable. It helps stabilizes that. And so it's kind of like this guy's in the vault, even though it's not in the vault, right? It's kind of like it's in the vault. So it's kind of like it's in this part here because it gives him that one extra electron to stabilize it. And so that's what happens with these guys. And in this case, it happens here too, because in that case, they're putting one in each orbital and it makes it a little more stable than if it was just, you had one, and then you had that one orbital that was empty. So it'll put one in each orbital in that case. So let me give you an example. Let's say we have mobidium, or actually let's do tungsten, because then that way we'll do a twofer. So if you guys can do me a favor, write what you guys would expect tungsten to be, and then we'll make a modification. Okay, tungsten. So now we're talking about tungsten.
And then for the short, please. The last parts that have changed are determining technical and
Okay, guys ready? Okay, so we're gonna go ahead and put tungsten. Okay, shortwave, what will be my core? Xe. Okay. Okay, so Xe is right here. So then we're gonna go 6s2. Then. Nope. Okay, so if we look at their atomic numbers, so this represents, that'll be 56, 55, 56. Where's 57 at? Okay, so then we have to go down here. Okay, so then it'll be 4F14. That's why I wanted to do this one. And then we come back. So we've done all of those. We come back up here. And we know that that represents this flag up here. Okay, and then that's 1 in the D, that's 2, that's 3, and that's 4. Okay, so normally we would think that we would do 5D4. Yeah, that look. Well, remember this one here, I wrote on the side that these actually belong in the D, those two, because the F can only hold 14, right? So if we count, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so these guys really are up here, but they make that gap, that empty hole, so that we know that they belong up there, where it belongs at. They're gonna belong to the D, that's right. So these guys belong to the D. So I had in the D right on the side. So only these right here. Okay. So that means that we have 4 in the D, right? Now, what really happens is it steals from the S and it'll put that in the D. Okay. So then what we'll have is we'll have W XE 6s2. Oops, sorry, 6x1, sorry, my bad. S1 for F14. And then 5D5. Okay. Okay. And it does that for all the ones that are in this row and all the ones that are in that row. So it always steals from the S in that case. Okay? Questions? Go ahead and ask. I said it does it for all of the elements that are in this row, So all of those elements, it'll always steal from the S. We'll take 1 from the S. And then all of the ones that are in this row, it'll also do the same thing.
S and it's gonna have 1.
That's right, the S is gonna have 1, and then the D is gonna have 5. because 5 it allows it. So what happens is, let me drop it for. So we know that how many orbitals are in the 5? I mean, in the D, sorry, my bad. Yes, how many orbitals are in the D? It has 5 orbitals. So we have 5 love seeds. 1, 2, 3, 4, 5. Right? So, and then we put this. Okay, and we're just gonna call this the 5B. Right? So now we know it has, normally it has 4. Right? So it does this, does this, does this, does this. So, and you know that the 6s is limited energy. How many orbitals does the 6s have? It has 1 orbital, that's right. So I have 1 level love state, right? So right now, this is the way it looks. We have an electron going in one direction, an electron going in the opposite direction. Right? They have opposite spins, being the same one. Okay, so then what it does, because it'll actually adjust its energy level. So it'll drop this guy down a little bit. We'll do this. It'll drop the energy level down. One, two, three, four, 5, and then it'll have its 6. So that 6 one is about the same energy level. And then it'll put those electrons in like this. So this is more stable than the other case, because if it has a choice, right? Each electron likes to be as far away from the other electron as it possibly can. Right? But we know that it has to fill those love seeds first. And in this case, it's a special case. I can sit there and act like I have each one of these love seeds at the same level, almost. Okay, so it does this instead. So all of the ones in that row, it'll be like row 11, I believe, right? Row 11. Yes, 6 and 11. Okay, so it's going to do that. So this will be in the case of row 6. In the case of row 11, it's like this. So it's like 1 away, and then it's like this. Okay? And then we have 1 here, right? So in that case, it definitely wants to do because it's like I just want 1, and then I have stability here. So it'll definitely take it from that. So then it'll bring them all to the same level, and then we'll do this. So we'll just go through that. So then this one, we can bend, right? Because it's a lot more stable to bend this one than to have than to put that other one. Okay. Okay. So how are we doing on time? Got some more stuff. We're doing good. Got some more stuff to go over. How are you guys feeling about this? Okay, good. Okay. So the next part is ions. We talked about ions. What are ions? I can't keep forgetting. Gain or lose of electrons, right? So it's elements or atoms that gain or lose electrons, right? So what happens if we're gaining and losing electrons? Where do they go? Right? That's what we should be asking ourselves, right? Where do they go? You know? So if I'm losing electrons, let me give you an example. Let me pull up my periodic table. Okay, so let's say we have let's do iron. So we have iron 2 plus. Fe 2 plus. So it'd be called iron 2. Okay, so in this case, we want to set it up as if we're doing Fe. So let's do Fe first. Let's do it the short way. Okay, so what would be the Fe the short way? It'd be helium. Are you sure? What would be the core? For Fe. Argon. So we're gonna have argon. So Fe's located here. And then we go to the noble gas that would be before. That'll be our noble gas before. So argon. Okay, so then we come down to this period. For S2. We have energy, so that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. So 3d6. Okay. So now when we're taking away electrons, we're gonna always take away from the highest period. Which one is the highest period? 4s2 or 3d6? Which one is the highest period? 4s2 or 3d6? 4s2, right? Because 4 is greater than 3, right? So we're going to take away from 4 first, okay? So then that means that this answer should be because we're removing 2 electrons. These electrons are being removed. Right? So when it's a plus, we're taking away electrons. Because remember, we're talking about electrons. Right? So that's what's happening here. Right? We're taking away those 2 electrons. And you always take away from the highest period first. Okay, so what if I had Fe 4 plus? So what am I gonna have then? Now, 4 is still gonna be the same, they are, because we're not stealing from there. Takes too much energy. And then 3d4. Okay, so you take away from the highest period first, and then you'd have to take the remainder from the next highest period. Okay, do you guys see how that works? You don't see how it works? Look at this number here. What number is bigger, 4 or 3? So then you're stealing from the bigger number first. It's kind of like this, okay? So when Bohr's rule is asked, right? The atom is here. The first period is here. Second period is here. Third period is here. Fourth period is here. This is the center of the atom. Now, this is like mom, right? The closer you are to mom, the more you're protected, right? The further away you are from mom, the less you're protected, right? So if your kid is really close, and say mom has her in 10, and child stealer comes, right? Is he gonna take the kid from that's close to mom, or is he gonna take the kid that's furthest away from mom? Furthest away. So we know that the 4S is furthest away. So you're gonna steal from that gate first. You're gonna steal that gate first because it's easier to take, right? The one that's across town rather than the one that's right underneath mom, right? And that's always the case. You're always gonna take the one that's furthest, then you're gonna take the one that's closest. Does that make sense?
Okay, why is it for, I mean, 3G instead of 4G?
Because in that case, it's FE4 plus, right? So 4 plus means what? You don't know, I don't know. Gotta help me out. What does 4 plus mean? I have 4 electrons that are being lost. They're removed, right? Because we know electrons are what charge? Negative, right? So then if I remove 4 negative, that means I have 4 positive. That's what I meant, right? So the 4 plus means I remove 4 electrons, right? If we look, Fe over here, if we look over here, Fe, that's what is neutral, right? So that's 2 electrons here, and then we also have 2 electrons that are being removed from here, right? So that's a total of 4, right? So that's where we get that 4. Does that make sense?
And I was talking about the 3D.
What about,
Like, on like
the 3 represents the, so 3 represents the period, right? So if we look where F is at, right, on our periodic table. This is where F is at, right? This is where F is at. We know that this one here is the 4th period. And then I told you guys that you're starting here. When you're here, this is the 3D, right? Okay, so we get 6 because there's 1, 2, 3, 4, 5, 6 electrons there. So then initially, when we're talking about Fe, there is 4s, 3d, 6, right? There's 2 in the 4s, 1, 2, and then there'll be 6 in the 3d. Does that make sense? Okay, so then when we take away electrons, we have to take away from the 4s first, and then we start taking away from the 3d. So in this case, we only took away 2 electrons. So we just take away that 4s. So that's how we ended up with this guy. Okay, and then this case, we're taking away 4 electrons. So we take away the 2 from here, and then we have to take 2 more from here, so that leaves me with just 4. 3d4. Does that make sense? Okay, so we've got to remember charges. What does those charges mean? If it's positive, that means we remove electrons. If it's negative, that means we're gaining electrons, right? So those are called ions. Positive ions are called positive. What was it? Positive ions are called, say cat ions. That's right, cat. That's right. Cat ions, right? Because they're positive. You guys can remember that. That's my joke. We'll remember. Pop, meow, pop, cat, meow, meow, positive, okay? And anions are negative, right? So negative ions are anions. So let's talk about the anion. So let's say we have selenium. Selenium 2 minus. Okay, for selenium, what is my core? We'll just do selenium by itself first. Then we'll do selenium 2 minus. So what would be the core for selenium? With the Se. Okay? Okay, and then, so that would be, we're looking for this guy over here. So then we'd write, got the argon, then we'd write what? What will be next after argon? 4s2. Okay, and then 3d10. And then 4p what? 4p4. Okay, so if I'm gaining 2 electrons, so what should be my answer then up here?
You're still gonna use the highest period?
What was that?
You're still gonna use the highest period?
The highest period. Okay, so in this case, are you going to use the highest period because you're adding electrons, right? So you're going to use the highest period because you're going to be adding electrons, right? So you're adding electrons, so then you should have 4s2 because you can only have 2 in the s. 3d10. Okay, that's it. Does that make sense? Okay, because you're adding 2 extra electrons. Yeah, you add to the one until it's full, and then if it runs over, then you go to the next one. Okay? Questions? Yes.
What if you have it? Like if you have it at the very end of like the very end of P, would you have to add on to like the next?
Yes, so if it runs over, you would run over to the next one. Doesn't happen, but if it did, it would run over to the next one. Because remember, your goal is to be like the noble gases, right? So once you get to your octet, you're usually like, I'm good. You can keep that and that's yours. You know? They're a little bit unlike us, you know, we want more and more money. They're like, no, once I reach my spot, I'm good. Okay, so let's go back to the lecture. You guys ready to go back to the lecture? Can't get that. We got 20 more minutes. I need to get that 20 minutes in. So does that make sense? Questions? There will always be questions like this in your next exam. Yes. Now you'll notice all the things that you guys have been learning, you're starting to use ions and all those things. So you want to make sure you know those definitions because they're going to be important for understanding the rest of the stuff, right? It's additive. Okay, so we've already talked about orbitals, right? So we know that the s orbital has 1 electron. I mean, the s has 1 orbital. The p has 3 orbitals, and the d has 5 orbitals, and the f has 7 orbitals. This is what it looks like. So this is what Bohr basically. So Bohr basically said that this is what was happening, that the electrons were orbiting in this way. Now, what they found out was that's not quite exactly what happens. So what really happens are these little spots here, more so, and it's very, very complicated. So let me show you how complicated it gets. So this here represents the shape of the orbital based upon imaging. Okay, so the electrons traveling around this, the nucleus. So the s orbital is just a sphere. The p orbitals, remember there are 3 orbitals for the p. So this is px, this is py, this is pz. So this one is in the x-axis, this one is in the y-axis, and that one's in the z-axis. This is the d, right? The d looks like 2 dumbbells put together, right? And then we have this really odd one where you have craziness going on here, right? And so that is the path that the electron travels in those orbitals. So that's what that represents. Okay? So you want to be familiar with the images. S is going to be simple, it's just going to be a sphere. The P orbitals, they're going to just look like dumbbells. The D looks like, you know, a 4-leaf clover, right? Except for that one that looks crazy. And the F is like insane. We don't even show you that, right? Now, the way it works is, have you guys played with Russian dolls? Do you guys know what Russian dolls are? Anybody not know what Russian dolls are? So they're the dolls that you put, like, you have a little doll on the inside, you have another one on the outside, you have another one on the outside, you have another one on the outside. Those are Russian dolls, right? So that little one fits inside. So the 1s will fit inside the 2s. And then the 2s will fit inside the 3s. And then that's the same thing with the p orbitals as well, too. So the 2p will fit inside the 3p, which will fit inside the 4p. So that's the same way it works. And so it's occupying the space, but it's sort of organized how it occupies that space. Now, this is the thing that you want to know. You get at least one question about Pauli exclusion principle. Now, Pauli exclusion principle basically says that no more than 2 electrons can occupy the same orbital. But you guys already knew that, right? So an orbital can only hold 2 electrons max. You can have 1 or you can have 2. That's it. 1, 2, or no, right? So you guys have already learned about electron configuration. You should be competent enough to do the homework problems for electron configuration. You're familiar with the periodic table and how to use the periodic table to do that electron configuration. So this is just showing you that path that you take, right? So 1s, 2s, 2. So this here is just showing you what one of the sublevels looks like. You guys take a look at this. What's that kind of look like? It looks like a D that forgot the top parts, right? So it's imaging the center part of the D. So you guys are already familiar. You always start off with the principal quantum number or the principal energy level, the period, right? In front, we have the sublevel, and then you have the number of electrons that you have in that sublevel. This here just shows you the electron configuration for some of the earlier atoms. We've already talked about how to use the core, right? And this just shows you that you know how to do that. You guys already know how to write electron configuration. You've been doing it, so we won't even worry about those problems. You've done that before, right? You can look at them as notes for later on to remind you. And yours were a lot harder than the ones that they give here. So I talked to you guys about the exceptions as well too, right? So at the end of the day, what we're looking at, we're trying to figure out which electrons are going to be available for reactors. We're trying to figure out our valence electrons. Okay, so when we talk about valence electrons, those are going to be the electrons that are going to be available for reactors. Okay, now primarily we're going to be talking about the main group. Now, when we're talking about the main group, we're only going to be looking at the s and the p orbitals. Again, I will repeat that because you're going to look at me like I'm crazy later on. When we're talking about the main group, we're talking about and P. Which groups are the main groups? You guys remember? What was that? S and P, yes. So those are gonna be the ones that are in the S and the P orbitals. We're just gonna add those two together, and then that's gonna represent our valence electrons. So if you guys can do me a favor, how many valence electrons does carbon have? If we're just looking at the S and the P in that outer shell. Nope, that's it. Was it? 4, that's right. Because we're only looking at that outer shell. So we're looking only in the 2, period, the second period, right? This is a carbon in the second period, right? So how many valence electrons does oxygen have? Well, somebody else, you can't tell me, somebody else. 6, okay? And how many valence electrons does chlorine have? Again, we're only looking at the S and the P. And that last shell that it's in. What was that? Fluorine. 7, that is correct. Okay, what about, let's see. What about tellurium? Tellurium. Again, we're only looking at S and P. Tellurium. 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 It's yeah, worse. Was that 6? That is correct, because we're only looking at the S and the P, right? So you're only going to count the S. 1, 2, 3, 4, 5, 6. Okay? So let me get you guys on the periodic table so you guys can see what we're doing, just in case. What was that? Okay, so let's see. Okay, so what we're going to be doing, we know where's the S? Which 2 groups represent the S? 1 and 2. Which groups represent the P? Okay, so we have tellurium. We're only going to count the S and the P. There's tellurium. So how many do we have in the S? So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. So we have 6 electrons to work with tellurium. Okay, does that make sense? Okay, so you guys see how that works. We're looking at the S and the P. Now, this is what happens for the main group. Transitional metals, right? Those are in the minor group. They're going to be special, right? So they're going to have special cases. So they're not going to try to obey the outside. They don't care about that. They have their own way to kind of figure out how to do stuff. Okay? So we're only going to be talking about the main groups. So that's going to be group 1, group 2, group 13, 14, 15, 16, and 18. 16, 17, and 18. We got 17. Working on counting today. Okay? How you guys feel? We're almost done. We're almost to the golden point. Okay, let me clear this. So when we talk about valence electrons, right? We know that the valence electrons are going to be the electrons that we're going to be able to use for reaction. So if you guys can do me a favor, sodium has how many valence electrons? We're looking at only the S and the P. It has 1, okay? So since we know that the most that we can have, if you guys can do me a favor, count all of the S and P total. How many spots do I have? If they were all out of the noble gas, how many spots would it be? Just counting S and P, one of the noble gases, except for helium special. 8. It has 8 spots, right? So I told you at the very beginning, everybody wants to be like the Johnsons, right? They want to be like the noble gases. So these guys all want to be like the noble gases. So the one in the main groups, they're trying to get to 8. So what we're gonna do is we're gonna use that 8 as our magic number. We call it the octet, right? So we figure out how many electrons that each one have to use to try to get to their octet. So we have sodium. Sodium has 1 valence electron, right? So the way that we do that, we would draw a Lewis structure. So the Lewis structure is just putting dots. You put the number of dots around it that it has valence electrons. So sodium has 1 valence electron. Magnesium, how many valence electrons does it have? 2. It has 2 dots around it. What about aluminum? 3. So then we put 3 dots around it. Okay? So if you guys take a look here, we're just putting dots around it to represent the number of valence electrons. So this is called the Lewis structure or the Lewis symbol. Okay? I call it the Lewis dot structure, right? Because that's what I learned it as, right? So I just keep adding stuff to it, right? Okay, so this is gonna help us when we try to figure out how things are gonna react, okay? So you wanna be able to identify the number of valence electrons, and then you're just gonna put that many dots around it, okay? Oxygen would have how many dots around it? Oxygen would have how many dots around it? How many? How many? 6, because we count the S and the P, right? So if you count only the S and the P in that level where oxygen is at, it's 6. Okay? Does that make sense? Okay, what about, let's see, how many dots would iodine have around it? 7. That's right. Okay? Okay, so this question always ends up being on the test and one of the multiple choice questions. I think it's a weird question, but in this case, all they want you to do is write a generic form for what they're talking about. So we're talking about group 16. So we want to know basically how many valence electrons, how many electrons are you going to have in the S, and how many are you going to have in the P for all of the ones that are in group 16. Because it should be exactly the same, right? Because they're all in the same group. So how many valence electrons should we have in the S for group 16? We should have 2. So then what you're going to write, you're going to write N S 2. And then how many should be left over in the P? For 16? For 4. I was like, what? Sorry. So we want P4, sorry, P4, NP4. Let me erase that. So it should be NP4. There we go. Okay, so if I'm talking about NS2, NP2, which group am I trying to talk about? You just told me that 16 was NS2, NP4. How can it be both of those? It can't be both. You're saying you have 2 electrons in the P, right? And you have 2 electrons in the S. So then that should be which group? Which group would have 2 electrons in the P and 2 electrons in the S? So start with the S. What was that?
14.
Group 14. That is correct. So all you do is just count over, count the electrons, right? So how many electrons is that? 2, right? Now let me do it on this. So we have 2 electrons here and 2 electrons there. So you just count over 2 and then 2 in the P, right? That's all you gotta do. Don't make it harder than what it is. Okay? And that's an easy one to make harder than what it is. You don't know how many people. I will tell you guys this. This is gonna be on the test. It will always be on the test. It's always. Always, you always get one question like this. That's a gimme question. And I'm gonna say about 70% of the students get it wrong. Because they overthink it. Don't overthink. Okay, so we've already talked about the Lewis symbol. You guys already know what it means, right? It means the valence electrons. Okay? So we've also talked about the octet, right? Noble gases are going to have octet. Now, helium is special. Its octet is 2. And hydrogen is going to want to try to be like helium. It only wants 2. It can't have 8 around it. It's not big enough to have 8. It's tiny. Have you guys ever seen a little kid, like a little kid carrying all this big stuff with a really big ass backpack going to school, like them all got from the backpack over a full grown person, and that little kid is like this, you know? You ever seen that? So that's what it's like. It can only hold 2. Okay, so there are trends that you need to be aware of. Some of the trends that you need to be aware of is atomic size. So as we move from the left-hand side to the right-hand side of the periodic table, right? The atom is going to get smaller. Okay. So, and then as we move from the top to the bottom, the atom gets bigger. Okay. So our biggest atom is going to be who? Look at the periodic table. So I said as we move from the left-hand side to the right-hand side, we get smaller. And then as we move from the top to the bottom, they get bigger. So which one? So just give me one atom. I don't care what it is. Just tell me the atom. What is the biggest atom? Who has the biggest butt? Who? Are you sure? Okay, so I'll say this again. As we move from the left to the right, our atom gets smaller. As we move from the top to the bottom, our atom gets bigger. Francium, right? Think about what I just said. So move from the left to the right, it gets smaller. So as we go from here to here, it gets smaller, right? And as we go from here to here, it gets bigger, right? So who's gonna have the biggest butt? Other than me. So let me put my periodic table because it helps. It helps see. Okay, so I said as we move from left to right, it gets smaller. Okay? And then as we move from top to bottom, it gets bigger. Okay? So we know that francium will be the biggest. Okay, so let's see if you guys can make any sense of this. Over. Okay. So you have to leave the trends to yourselves. Okay, so you guys have to work on your own trends. We'll talk about it a little bit next week, and then we'll finish it up next week. So we're stopping here.